You're an astronaut, and you're tumbling helplessly through the most incomprehensible expanse of darkness that exists anywhere in the known cosmos. This isn't just empty space. This is a region so profoundly void of matter, so utterly devoid of light, that it defies every instinct your brain has about what the universe should look like. There are no stars here, no planets, no galaxies, no clouds of gas or dust. Nothing but cold, silent emptiness stretching in every direction for distances that make interstellar space look crowded by comparison. This is the Boötes Void. Some astronomers call it the Great Nothing. And unless you somehow find your way back to your spacecraft, you're going to be drifting through this perplexing ocean of absolute darkness for timescales that dwarf human civilization. Actually, let me correct that. You won't be drifting. Your frozen, lifeless body will be drifting, because out here, hundreds of millions of light years from the nearest help, there's nobody coming to rescue you. There's nobody even nearby to know you exist. And here's what makes this whole situation even more surreal. You've been looking at this void your entire life. Every time you've gazed up at the night sky, you've been staring directly at it without even knowing it was there. Go outside on a clear night. Look toward the northern sky. Find the Big Dipper, that familiar pattern of stars that's been guiding travelers and inspiring stories for thousands of years. Now locate Arcturus, the brilliant red giant that ranks as the fourth brightest star visible from Earth. Stretch an imaginary line between them. Right there, in that seemingly ordinary patch of darkness, lies one of the most extraordinary features in the entire observable universe, the Boötes Void. A cosmic cavity so massive that it could swallow millions upon millions of galaxies the size of our Milky Way. From Earth, you can barely detect it. You might notice that the stars seem a little less dense in that region, but that's about it. Our telescopes had to reveal its true nature. And once they did, astronomers were left scratching their heads, because what they found shouldn't really exist on this scale. But it does exist. And right now, in this scenario, that's exactly where you're headed. So let's explore what it would actually be like to fall into this incomprehensible ocean of nothing. What would you see? What would you feel? And perhaps most importantly, how would you even get there in the first place? Well, the first challenge you'd face is the journey itself, because the Boötes Void isn't just far away. It's far away in a way that makes interplanetary travel look like a walk to the corner store. We're talking about a distance of 700 million light years from Earth. 700 million. Let me give you some context for just how absurdly distant that really is. The Andromeda Galaxy, which is our nearest major galactic neighbor, sits about 2.5 million light years away. That's already a distance so vast that light itself, traveling at 186,000 miles per second, takes 2.5 million years to cross it. The Boötes Void is 280 times farther away than Andromeda. 280 times. Even if you could somehow travel at the speed of light, which, according to everything we understand about physics, is impossible for anything with mass, it would still take you 700 million years just to reach the edge of the void. To put that in biological perspective, that's roughly the same amount of time it took for complex animal life on Earth to evolve from simple sponges in the primordial oceans all the way through fish, amphibians, reptiles, the age of dinosaurs, the rise of mammals, and eventually to human beings standing here today. Now let's talk about trying to get there using our actual, current technology. The fastest spacecraft humanity has ever built is the Parker Solar Probe. This remarkable machine can reach speeds of about 430,000 miles per hour as it whips around the Sunday. That sounds incredibly fast, and it is by human standards. But in cosmic terms, it's barely moving. The Parker Solar Probe travels at roughly 0.05% of the speed of light. At that velocity, the journey to the Boötes Void would take over 1 trillion years. 1 trillion. For context, the entire universe is only about 13.8 billion years old. You'd need the universe to age roughly 72 times longer than it already has just to complete this journey. And that's assuming the spacecraft could even survive that long, which it absolutely couldn't. Plus, the Parker Solar Probe has no life support systems, no crew quarters, no food or water supplies, and nowhere to sit. It's just a probe packed with scientific instruments designed to study the Sunday. So for the purposes of this thought experiment, we're going to have to imagine that you have access to a spacecraft with capabilities far beyond anything that exists today. A ship that can somehow accelerate to speeds approaching the speed of light. A ship with life support systems that can sustain you for hundreds of millions of years. Or perhaps some kind of suspended animation technology that lets you sleep through the journey. This is firmly in the realm of science fiction, but without it, this trip is completely impossible even to imagine. All right. You climb aboard your hypothetical faster-than-light spacecraft. You punch in the coordinates for the Boötes Void. You engage the engines, and you prepare to leave Earth behind forever. But here's the thing about leaving Earth. Actually getting away from our planet is the easy part. We've been doing that since 1961. The real challenge is leaving the solar system itself. You can't just point your spacecraft away from the sun and hit the accelerator. The physics doesn't work that way. Everything in our solar system, from the smallest asteroid to the largest planet, is gravitationally bound to the Sunday. Earth orbits our star at a speed of about 67,000 miles per hour, or roughly 30 kilometers per second. That might seem fast, but it's exactly the right speed to maintain a stable orbit at our distance from the Sunday. To actually escape the sun's gravitational influence, your spacecraft needs to reach what's called escape velocity, which depends on how far you are from the Sunday. And here's where things get interesting. You can't just fly in a straight line away from the solar system. The most efficient way to escape is to use what's called a gravity assist trajectory. Essentially, you'd make a series of increasingly wide spirals around the sun, each orbit taking you a little farther out. Maybe you'd swing by Jupiter or Saturn to steal a bit of their orbital momentum, giving yourself an extra boost. Gradually, orbit by orbit, you'd loosen the sun's grip until finally you'd reach a point where its gravity could no longer pull you back. No problem, right? You've got your impossibly advanced spacecraft. You've got time. Well, you've got all the time in the world, actually, because this journey is going to take a while. As you venture farther and farther from our solar system, pushing out beyond the orbit of Neptune, past the Kuiper Belt where Pluto and countless other icy bodies reside, and eventually into the realm of the Oort cloud, that vast spherical shell of comets that marks the true edge of the sun's domain, you'd start to notice something profound. The sky is changing. Near Earth, when you look up at night, you see hundreds or even thousands of stars depending on how dark your skies are. That's because we're embedded inside the Milky Way galaxy, surrounded by somewhere between 100 and 400 billion stars, many of which are close enough to be visible to the naked eye. The Milky Way is our cosmic neighborhood, and from our perspective inside it, the galaxy appears as a bright band stretching across the sky. But as you leave the solar system and eventually exit the Milky Way entirely, those stars begin to disappear from view, not because they're going out, but because you're moving away from them. Imagine walking away from a city at night. At first, you see thousands of individual lights, but as you get farther away, those lights merge together and dim, until eventually, the whole city is just a faint glow on the horizon. That's what leaving the Milky Way would be like. Our galaxy is enormous. It stretches approximately 100,000 light-years from edge to edge. Earth sits roughly 26,000 light-years from the galactic center, about halfway between the core and the outer rim. Even traveling at near-light speeds in a straight line, it would take you 26,000 years just to reach the edge of the galaxy. Think about that for a moment. The entire span of recorded human history, from the first written languages in ancient Mesopotamia to the smartphone in your pocket, is only about 5,000 years. You'd need more than 5 complete cycles of human civilization just to exit our galaxy. But eventually, after those 26 millennia of travel, you'd cross that invisible boundary. And the moment you left the Milky Way behind, your view of the cosmos would transform completely. The countless stars that had surrounded you would suddenly be gone, replaced by a handful of fuzzy patches of light scattered across the darkness. Those patches are other galaxies: Andromeda, Triangulum, the Magellanic Clouds, entire island universes, each containing billions or trillions of stars, now appearing as nothing more than smudges against the black. You'd continue onward. Millions of years would pass. You'd leave our local group of galaxies behind. Then the Virgo supercluster, that massive collection of galaxy groups and clusters to which the local group belongs. You'd sail past galaxy after galaxy, watching as they slowly drift by like distant ships on an infinite ocean. And then, finally, after eons of travel, you'd approach the last major structures before the void. The constellation Ursa Major, which contains the Big Dipper, marks one of the boundaries. You'd see the final galaxy clusters, the last outposts of matter before the great emptiness begins, and beyond them, nothing. The backdrop of space would transition from the faint glow of distant galaxies to absolute, total blackness. But here's the thing that really drives home the scale of what you're dealing with. Even after all that travel, even after crossing 700 million light-years of space and finally reaching the edge of the Boötes Void, you'd still have an astronomical distance left to go. Because the Boötes Void isn't just a gap between galaxies. It's a spherical region of space measuring approximately 330 million light-years in diameter. It's the largest void structure ever discovered in the universe. To cross from one edge to the other would require another 330 million years of light-speed travel. To reach the center, the heart of the void where the emptiness is most profound, you'd need to travel 165 million light-years from the edge. Let's convert that to more familiar units just to appreciate the absurdity. 165 million light-years equals roughly 970 sextillion miles. That's 970, followed by 21 zeros, or if you prefer kilometers, about 1.5 septillion. These numbers are so large they've lost all practical meaning. The human brain simply isn't equipped to comprehend distances on this scale. This is why astronomers call it the Great Nothing. It's not just empty, it's empty on a scale that defies imagination. So, let's say you've decided to continue anyway. You cross the threshold from the last galaxy clusters into the void itself. What would that transition feel like? The answer might surprise you. It wouldn't feel like anything at all. There'd be no sudden drop, no pull of gravity, no sense of crossing a boundary. Space doesn't have edges in the way we normally think about them. The void isn't a hole you can fall into. It's just a region where matter happens to be extraordinarily sparse. Entering it would be as subtle as passing from one room into another in complete darkness. One moment, you'd be in a region with an occasional distant galaxy visible in your instruments. The next moment, there'd be nothing at all. As you venture deeper into the Boötes Void, heading toward its center, the darkness would become absolute. Not dark like a moonless night on Earth. Not dark like a cave, deep underground. Dark like nothing you've ever experienced. Dark in a way that's almost aggressive in its completeness. With the naked eye, you wouldn't be able to see a single star. Not one. In every direction you looked, there would be nothing but blackness. The closest galaxy to the center of the Boötes Void is more than 10 million light-years away. And here's the cruel trick of cosmic distances. Even a relatively bright galaxy at that range would be far too faint for human eyes to detect without technological assistance. Think about what that means for a moment. Throughout human history, no matter where people have lived on Earth, they've always had the stars. The night sky has been a constant companion, a source of wonder, navigation, mythology, and inspiration. Ancient sailors used the stars to cross oceans. Desert travelers used them to find their way across endless sand. Our ancestors looked up and saw patterns, created stories, built entire cosmologies around those distant lights. The stars have been our connection to something larger than ourselves, a reminder that we're part of a vast universe. In the center of the Boötes Void, all of that would be gone. There would be no stars to navigate by, no constellations to recognize, no Milky Way arcing overhead. Just pure, unbroken darkness in every direction. If you've ever experienced true sensory deprivation, maybe in a flotation tank or in a deep cave where all light has been extinguished, you might have some small sense of what this would be like. Except in those cases, you're floating in warm water or standing on solid ground. You have points of reference. Your body can feel gravity, can sense up from down. In the Boötes Void, even those basic orientations would be gone. You'd be in microgravity, the same condition astronauts experience on the International Space Station. Without nearby massive objects like stars or planets, there'd be essentially no gravitational pull in any particular direction. You wouldn't feel weight. You wouldn't feel like you were falling, even though in a sense you'd be in perpetual freefall. There would be no up, no down, no sense of motion, unless you could see something to move relative to, and you couldn't see anything. That's the point. In other parts of space, even in the vast emptiness between galaxies, you'd at least have some distant light sources to give you a frame of reference. You could watch stars slide past your field of view and know you were moving. You could orient yourself relative to some distant galaxy. Not here. Here, if your spacecraft's lights failed, if your instruments powered down, if you were left floating in your spacesuit with nothing but the universe around you, you would lose all sense of direction and distance. You could be rotating slowly, tumbling end over end, and you'd have no way to know it. You could be moving at tremendous speed or hanging perfectly still in space, and the view would be exactly the same, nothing. It would be the ultimate sensory deprivation experience. Just you and the void. You and the silence. Because yes, it would be utterly silent. Sound requires a medium to travel through. Molecules of air or water or some other substance that can vibrate and carry acoustic waves. Space is a vacuum. Not a perfect vacuum, because there are always a few scattered atoms of hydrogen and helium drifting around, but close enough that sound cannot propagate. You could scream at the top of your lungs inside your helmet, and the sound would bounce around inside your suit, but nothing outside would hear it. The void wouldn't notice. It wouldn't care, and it would be cold. Unimaginably cold. The temperature of deep space far from any stars hovers around 3 degrees Kelvin. That's 3 degrees above absolute zero, the coldest possible temperature in the universe. In more familiar units, we're talking about negative 270 degrees Celsius, or negative 454 degrees Fahrenheit. At these temperatures, almost everything freezes solid. Gases become liquids. Liquids become solids. Molecular motion slows to almost nothing. Your spacesuit would need insulation beyond anything we currently possess just to keep you alive. And if that insulation failed, if there was even the smallest breach in your suit, the cold would kill you faster than the lack of oxygen. Your body heat would radiate away into the void within minutes. You'd freeze solid, preserved perfectly in the cosmic deep freeze for billions of years. But let's assume your suit is working perfectly. Let's assume you have everything you need to survive. What would the psychological experience be like? Humans are not evolved for this kind of environment. Our brains developed on the African savanna, in a world full of visual landmarks, sounds, tactile sensations, and constantly changing stimuli. We're adapted to navigate through forests and across plains, to recognize patterns, to orient ourselves using the sun and stars and landscape features. Take all of that away, and the human mind starts to do strange things. Sensory deprivation experiments here on Earth have shown that when people are deprived of normal sensory input for extended periods, they begin to hallucinate. The brain, desperate for something to process, starts generating its own sensations. People report seeing lights, hearing sounds, feeling phantom touches. Some experience vivid dreamlike states. Others lose their sense of time entirely, unable to tell if minutes or hours have passed. And those experiments last hours or maybe days. You'd be in the Boötes Void for far longer than that, assuming you had some way to survive. Would you go mad? Would your mind fracture under the weight of endless, unchanging darkness? Or would you somehow adapt, finding a kind of peace in the absolute stillness? Maybe, if you were lucky, you'd have sophisticated instruments in your spacesuit. telescopes sensitive enough to pick up the faintest whispers of light from the edges of the void. If you had equipment like that, you might be able to detect a few fuzzy smudges on the absolute horizon of your vision. Those would be the galaxies that mark the boundary of the void, tens of millions of light years away. Vast collections of billions of stars, reduced to barely perceptible glimmers by the sheer distance. And if your instruments were truly state-of-the-art, equipped with the most advanced detection technology imaginable, you might pick up something else. Something that would come as a surprise to anyone who thought the Boötes Void was completely empty. Because despite its name, despite its reputation as the Great Nothing, the Boötes Void isn't entirely devoid of matter. It's not a perfect vacuum. Astronomers have discovered that there are approximately 60 small galaxies scattered throughout this immense volume of space. 60 galaxies in a region that, if it had average cosmic density, should contain tens of thousands of them. Most of these 60 lonely galaxies are clustered together in a single filamentary structure that threads through part of the void. They're small galaxies, dwarf galaxies in many cases, containing perhaps a few billion stars each instead of the hundreds of billions you'd find in a galaxy like the Milky Way. And they're spread across such enormous distances that calling the void populated would be wildly generous. To put this in perspective, imagine the Pacific Ocean. Now imagine there are exactly 60 goldfish swimming somewhere in that entire ocean. What are the chances you'd ever encounter one if you were dropped randomly into the Pacific? Essentially, zero. That's what it would be like looking for those galaxies in the Boötes Void. You could wander for millions of years and never come across one. So realistically, if you fell into the void, if you became separated from your spacecraft and lost in that infinite darkness, those 60 galaxies wouldn't help you. You'd never find them. All you would experience is the blackness, the silence, the cold, the absolute total absence of anything. It would be like floating in the purest black ink imaginable. The color you see when you close your eyes in a completely dark room, except all around you, in 3 dimensions, extending forever in every direction. Vanta black, that substance scientists have created, that absorbs 99.9% of visible light, would be bright by comparison. This would be true darkness. The hexadecimal color code number 00000000, pure black, rendered in 3-dimensional reality on a cosmic scale. And you'd be alone. Completely, utterly, profoundly alone. In a way that few humans have ever experienced or even imagined. On Earth, even in the most remote locations, you're never truly isolated. There are bacteria in the soil beneath your feet, birds in the sky above you, fish in the deepest oceans. There's the planet itself, a massive ball of rock and metal surrounding you with its gravity and its presence. In the Boötes Void, there would be none of that. The nearest life, the nearest consciousness besides your own, would be hundreds of millions of light years away. If you sent out a radio signal calling for help, traveling at the speed of light, it would take 700 million years to reach Earth. And even if someone received it and immediately sent a rescue mission at light speed, it would take another 700 million years for them to arrive. By that time, Earth itself might not even exist anymore. The sun will eventually expand into a red giant and consume the inner planets, though that won't happen for another 5 billion years or so. But continental drift will have rearranged Earth's surface countless times. Species will have evolved and gone extinct. Human civilization, if it still exists at all, will be unrecognizably different. You'd be more isolated than any human being has ever been. More isolated than astronauts on the moon, who are only a few days' journey from home. More isolated than the most remote Antarctic researchers, who can at least radio for help and expect it to arrive within weeks or months. You'd be cosmically, absolutely, irrevocably alone. How would the human psyche handle that? Would the loneliness be crushing, a psychological weight that would break your mind? Or would there be a strange kind of peace in it? No obligations. No expectations, no noise or chaos or demands on your attention, just you and the infinite quiet of the void. Some people might find that horrifying. Others might find it almost meditative. Of course, the reality is that you probably wouldn't survive long enough to find out. Unless your spacesuit had some kind of miraculous power source and life support system that could sustain you indefinitely, you'd run out of oxygen within hours. Even the most advanced spacesuits ever designed can only provide breathable air for about 8 hours before their reserves are exhausted. After that, you'd suffocate. Your body would drift on, a frozen monument to cosmic exploration, gone horribly wrong, tumbling slowly through the darkness for billions of years. But let's push the thought experiment even further. Let's imagine you somehow had a suit that could keep you alive indefinitely. Fusion-powered maybe, with perfect recycling systems that could extract oxygen from your exhaled carbon dioxide forever, that could synthesize water and nutrients from the trace elements in space. It's pure science fiction, but let's run with it. In that case, you might drift in the void for geological timescales. Millions of years. Tens of millions of years. What would happen over those vast stretches of time? Well, the universe would be changing around you, even if you couldn't see it. Galaxies would be moving, carried along by the expansion of space itself. The expansion of the universe, driven by dark energy, would be pushing those distant galaxy clusters farther and farther apart. The void would be getting bigger, emptier, more profoundly isolated. Eventually, billions of years in the future, the universe's expansion will have carried distant galaxies so far away that their light can no longer reach us. The observable universe will shrink. If you waited long enough in the Boötes Void, even those 60 scattered galaxies would eventually disappear from view, their light stretched and redshifted into oblivion. But you'd still be there, drifting, unchanging, waiting, alone in the dark. Now, you might be wondering at this point, how did we even discover this thing in the first place? How do you find something that's defined by the absence of everything? The story of the Boötes Void's discovery takes us back to the late 1970s and early 1980s. During that era, astronomers were working on an ambitious project, creating a three-dimensional map of the universe. Up until that point, we'd known where galaxies were located in the sky, their positions in 2 dimensions as we see them from Earth. But we didn't have accurate information about how far away they were, their distances in the 3rd dimension. To build that 3-dimensional map, astronomers used a technique based on the Doppler effect. You're probably familiar with the Doppler effect from everyday life. It's the reason a car's engine sounds higher-pitched as it approaches you and lower-pitched as it drives away. The sound waves get compressed as the source moves toward you and stretched out as it moves away. Light works the same way. When a light source moves toward you, its light waves get compressed, shifting toward the blue end of the spectrum. When it moves away, the waves stretch out, shifting toward red. And because the universe is expanding, almost every galaxy we can see is moving away from us, which means their light is redshifted. The farther away a galaxy is, the faster it's receding from us due to cosmic expansion, and the more its light is redshifted. By measuring how much a galaxy's light has shifted toward the red end of the spectrum, astronomers can calculate approximately how far away it is. It's not a perfect measurement, but it's good enough to build a rough 3-dimensional map of cosmic structure. So these astronomers in the late 70s and early 80s were painstakingly measuring the redshifts of thousands of galaxies, plotting their positions in 3-dimensional space, trying to understand how matter was distributed throughout the universe. And as they worked, they started noticing something strange. In one particular region of space, in the direction of the constellation Boötes, there was a conspicuous absence of galaxies. At first, they thought it might be an error, a problem with their instruments or their data. Maybe there was some kind of dust cloud blocking their view, making it seem like there were no galaxies when really they were just hidden. But as they gathered more data, the picture became clearer. There really were almost no galaxies in that region. It wasn't an observational artifact. It was real. They discovered a void, an enormous, roughly spherical region of space measuring hundreds of millions of light years across, containing almost no galaxies whatsoever. It was far larger than any void that had been detected before. In fact, It was so large that it seemed to challenge some existing ideas about how the universe should be structured. The discovery was published in 1981, and it sent ripples through the astronomical community. How could something this big and this empty exist? What did it mean for our understanding of cosmic structure? To answer those questions, we need to zoom out and look at how the universe is organized on the largest scales. And it turns out that the structure of the cosmos is far stranger and more intricate than you might imagine from just looking up at the night sky. When you gaze at the stars on a clear night, it might seem like they're scattered randomly across the sky, sprinkled evenly throughout space like sugar on a tabletop. But that's an illusion created by our limited perspective. The universe isn't arranged randomly at all. On the largest scales, it's organized into a structure that astronomers call the cosmic web. Imagine a three-dimensional spider's web stretching across the entire observable universe. The threads of this web are made of galaxies, galaxy clusters, and enormous galaxy superclusters. These structures form long, thin filaments and broad, flat sheets that stretch for hundreds of millions of light years. Where the filaments intersect, you get massive nodes containing thousands of galaxies packed relatively close together. These are the galaxy clusters and superclusters, the densest regions of the cosmic web. Between the filaments and sheets, there are gaps. Vast, empty bubbles where almost no galaxies exist. These are the voids, and they make up the majority of the universe's volume. To visualize this better, think about foam. Not the rigid foam you might use for insulation, but something more fluid and delicate. Imagine soap bubbles forming in a sink full of dishwater. As you squeeze more soap into the water and agitate it, bubbles form and multiply. From a distance, the foam seems to fill the sink, taking up a huge volume. But if you look closely, you realize that the actual soap and water are concentrated in thin films between the bubbles. Most of the volume is just air. The universe is structured the same way. All the galaxies, all the stars, all the visible matter in the cosmos is concentrated in the thin films and filaments of the cosmic web. The bubbles, the empty spaces between those filaments, are the voids. And just like with soap foam, the voids actually make up most of the universe's volume. Astronomers estimate that cosmic voids account for roughly 80% of the total volume of space. So the universe is mostly empty. Vast regions of nearly pure vacuum, punctuated by dense filaments and clusters of matter. It's a strange counterintuitive structure. Nothing like the uniform distribution of matter you might expect. But why? Why is the universe organized this way? What process could create such an elaborate cosmic architecture? The answer lies in gravity, that fundamental force that keeps your feet on the ground and the Earth in orbit around the Sunday. Gravity has been shaping the universe since the very beginning, sculpting matter into the patterns we see today. Let's go back to the start. About 13.8 billion years ago, the universe began in an event we call the Big Bang. In its earliest moments, the universe was incredibly hot, incredibly dense, and filled with a nearly uniform soup of energy and matter. But it wasn't perfectly uniform. There were tiny fluctuations in density, microscopic variations in how much matter existed in different regions of space. Some areas had slightly more matter than average. Others had slightly less. These tiny differences might seem insignificant, but gravity amplified them over time. Regions with slightly more matter had slightly stronger gravitational fields. That stronger gravity pulled in more matter from surrounding regions, making those areas even denser. The dense regions got denser. Meanwhile, the less dense regions lost matter to their denser neighbors, becoming even more depleted. This process is called gravitational instability, and it's been operating throughout cosmic history. Over millions and billions of years, the small initial fluctuations in matter density grew into larger and larger structures. Gravity pulled matter together into clumps. Those clumps merged to form larger clumps. Stars formed, then galaxies, then clusters of galaxies, then superclusters, stretching across hundreds of millions of light years. At the same time, the regions between these dense structures became increasingly empty. As matter flowed toward the filaments and nodes of the cosmic web, it drained away from other areas, leaving behind vast voids. It's a bit like watching water drain from a bathtub. At first, the water is distributed fairly evenly, but as it drains, it starts to swirl and form patterns. Most of the water flows down the drain in a spiraling current, while other areas of the tub become dry. The cosmic web formed through a similar process, with matter flowing along gravitational currents toward the densest regions, leaving voids in between. The Boötes Void is simply one of the largest bubbles in this cosmic foam. It formed the same way all voids form, through billions of years of matter being gravitationally pulled away toward denser surrounding regions. Early in the universe's history, that region of space happened to have slightly less matter than average. Gravity did the rest, draining away most of what little matter was there and leaving behind the enormous cavity we see today. Those 60 or so galaxies that do exist within the void? They're probably remnants, small concentrations of matter that managed to collapse and form galaxies before all the matter in the region was pulled away. Or they might be galaxies that formed along a thin filament threading through the void, one of those rare structures where enough matter remained to ignite star formation. But overall, the Boötes Void is empty, because gravity made it that way. It's a natural consequence of how cosmic structure forms and evolves over billions of years. And it's not unique. Astronomers have discovered thousands of voids throughout the observable universe. Some are smaller, measuring only tens of millions of light-years across. Others are comparable to the Boötes Void in size. There might be even larger voids out there that we haven't discovered yet, hidden in regions of space we haven't surveyed thoroughly. In fact, if you mapped out the entire observable universe in 3 dimensions with all these voids included, you'd see that empty space isn't the exception, it's the rule. The cosmic web is mostly emptiness, with matter concentrated in a delicate lacework of filaments and nodes. We happen to live in one of those filaments, surrounded by relatively nearby galaxies, which gives us a skewed perspective. From our vantage point inside the Milky Way, space seems rich with stars and galaxies. But most of the universe doesn't look like our neighborhood. Most of it looks like the Boötes Void. So what would it really be like to fall into the center of that supervoid? We've covered the physical experience, the darkness and cold and isolation. But let's think about the philosophical dimension for a moment. There's something profoundly humbling about contemplating a place like the Boötes Void. It forces us to confront the sheer scale of the universe and our own cosmic insignificance. We live on a small rocky planet, orbiting an average star in an ordinary galaxy. That galaxy is part of a small cluster, which is part of a larger supercluster, which is just one tiny strand in the vast cosmic web. And even that web, with all its billions of galaxies, occupies only a fraction of the universe's volume. Most of space is empty. From the center of the Boötes Void, even our galaxy, which seems so vast and important from our perspective, would be invisible. The Milky Way would be one of countless galaxies, hundreds of millions of light-years away, too distant and too faint to see. All of human history, every civilization that has ever existed, every person who has ever lived, every thought and dream and achievement of our species would be utterly invisible from that vantage point. We would be less than a speck of dust. We would be nothing. And yet, despite that cosmic insignificance, there would be something almost serene about the void, a kind of ultimate simplicity. No complexity, no chaos, no noise, just pure, undisturbed emptiness. In a strange way, it might be the most peaceful place in the universe. No conflicts, no struggles, no entropy wearing things down because there's nothing there to wear down in the first place. If you were floating there with a spacesuit that could sustain you indefinitely, you might have time to think in ways that would be impossible in the busy, stimulating environment of normal life. No distractions, no interruptions, nothing but you and your thoughts and the infinite dark. Some people would find that maddening. Others might find it meditative, almost transcendent. It would depend entirely on the individual. Of course, the reality is that none of this is actually possible. We can't travel to the Boötes Void. We can't even come close with current or foreseeable technology. The distances are simply too vast. The energy requirements too enormous. Humanity will probably never visit the Boötes Void. We'll probably never even visit another galaxy, let alone a region of space 700 million light-years away. But we can observe it. We can study it with our telescopes. We can map its extent, measure its properties, use it to test our theories about how the universe works. The Boötes Void might be unreachable, but it's not unknowable. And in some ways, that's the beauty of astronomy. We can explore the cosmos without ever leaving Earth, using nothing but light and mathematics and human curiosity. The void teaches us about structure and evolution on cosmic scales. It shows us that the universe is far stranger and more textured than we might imagine. It reminds us that emptiness is just as much a part of the cosmos as matter and energy. You can't have one without the other. The voids define the filaments, and the filaments define the voids. They're two sides of the same cosmic architecture. And maybe there's a lesson in that for us. Maybe the empty spaces in our own lives, the quiet moments, the periods of solitude and reflection are just as important as the busy, productive times. Maybe we need both to be complete. The Boötes Void certainly suggests that emptiness has its place in the grand scheme of things. But let's bring this back down to the practical level. If you somehow did fall into the Boötes Void, if you became lost in that cosmic ocean of darkness, what would actually happen to you? Your body, assuming it's inside a spacesuit, would drift. For millions of years, billions of years, possibly trillions of years, you would tumble slowly through the void. The expansion of the universe would carry you along with it, gradually stretching the space between you and everything else. Eventually, even if someone came looking for you with impossibly advanced technology, they might not be able to find you because space itself would have expanded so much that you'd be beyond their reach. Your body would be preserved perfectly in the cosmic deep freeze. At 3 degrees Kelvin, there's no bacterial decay, no chemical processes that would break down your tissues. You'd be frozen solid, a monument to cosmic exploration, drifting through the dark until the end of time itself. And what is the end of time in this context? Well, that depends on how the universe ultimately ends, which is still a subject of scientific debate. If the universe continues expanding forever, driven by dark energy, then eventually all the stars will burn out, all the galaxies will drift beyond each other's horizons, and space will become cold, dark, and empty everywhere. The entire universe will become one vast void. Your frozen body would drift through that final darkness forever, or at least until even atoms themselves decay, trillions upon trillions of years in the future. Alternatively, if dark energy behaves differently than we think, the universe might eventually stop expanding and collapse back on itself in a big crunch, the opposite of the Big Bang. In that case, all matter would be drawn back together. Space itself would contract, and eventually everything, including your drifting body in the Boötes Void, would be compressed into an infinitely dense point. Not a pleasant end, but at least it would be an end. Either way, falling into the Boötes Void would mean drifting alone through the darkness for timescales that make human history look like a fleeting instant. It would be the ultimate isolation, the final frontier taken to its most extreme conclusion. So maybe, just maybe, the Boötes Void is a place we should admire from a distance, a cosmic wonder to study and contemplate, but not to visit. There are so many other places we could explore that would be far more rewarding and far less terrifying. Our own solar system, for example, is full of incredible destinations we haven't fully explored yet. Mars beckons with its ancient river valleys and potential for past life. Venus challenges us with its hellish surface conditions and crushing atmospheric pressure. The moons of Jupiter and Saturn, worlds like Europa and Enceladus, might harbor liquid water oceans beneath their icy shells. And where there's water, there might be life. Titan, Saturn's largest moon, has lakes and rivers of liquid methane, an alien hydrological cycle unlike anything else in the solar system. Beyond our solar system, there are billions of exoplanets, planets orbiting other stars. Some of them are probably rocky worlds like Earth, orbiting in their star's habitable zone where liquid water could exist on the surface. Maybe some of them actually do harbor life. Wouldn't it be more interesting to explore those worlds than to drift through empty darkness? Even if we limit ourselves to pure observation, to studying the cosmos with telescopes rather than visiting it in person, there are so many more visually interesting and scientifically valuable targets than a void. Galaxy collisions, where two massive galaxies smash together over millions of years, triggering bursts of star formation and creating bizarre gravitational distortions. Quasars, supermassive black holes actively feeding on matter and blasting out jets of energy visible across billions of light years. Supernovae, the explosive deaths of massive stars that briefly outshine entire galaxies. Nebulae, vast clouds of gas and dust where new stars are being born. The universe is filled with wonders, active, dynamic, beautiful phenomena that capture the imagination and teach us about physics and chemistry and the nature of reality. The Boötes Void is interesting in its own way, certainly. It tells us about large-scale structure and cosmic evolution. But it's not exactly visually spectacular. It's just darkness, absence, nothing. And we've spent all this time talking about nothing. Literally. We could have discussed so many other topics that would have been more visually engaging, more immediately gripping. But there's something compelling about the void nonetheless. Maybe it's because it represents the ultimate unknown, the deepest possible isolation, the most extreme environment conceivable. Or maybe it's because contemplating that emptiness forces us to confront questions about existence and meaning and our place in the cosmos. Whatever the reason, the Boötes Void holds a strange fascination. It's a place defined entirely by what it lacks, and yet that absence is so profound, so absolute, that it becomes a presence in its own right. The great nothing is something, paradoxically, because of how thoroughly it is nothing. And so, there you have it. The Boötes Void, a spherical cavity 330 million light-years across, containing almost no matter, no light, no life. A place where you could drift for billions of years without encountering a single star. A place that's simultaneously the emptiest and, in its own way, one of the most thought-provoking locations in the entire observable universe. You wouldn't want to fall into it. You definitely wouldn't want to get lost there. But it exists, hanging in the northern sky between the Big Dipper and Arcturus, a testament to the strange and wonderful ways that gravity and cosmic expansion have sculpted the universe into the intricate, beautiful, terrifying structure we observe today. And now, every time you look up at that patch of sky, you'll know what's really there. Not stars, not galaxies, just darkness. The great nothing, the Boötes Void, waiting silently in the cosmic deep, empty and patient and eternal.